Okay, next up we have a rational inequality, which is solved in a similar way as our polynomial inequalities. We need to find those key points, which are points where our function could possibly be changing sign, and then set up our little intervals in our sign chart and figure out our result. So this one is already set up nicely for us. We have one side of the inequality is 0 and the other side is a single fraction. So we are ready to go to find our key points. We find the key points by setting both the numerator and the denominator equal to 0, because our function can change signs either at x-intercepts or where it is undefined. So to find out where the denominator equals 0, we're going to need to factor here. So to get a positive 5, we would need a +7 and a -2. So we end up with key points, the -5 from the numerator, a 2 from the denominator, and a -7 from our denominator. So we take those key points and we put them on our number line, smallest to largest. Otherwise, the scaling doesn't really matter. We do just want to make sure they're in order, smallest to largest. And this time that sets us up with 4 intervals that we need to test. We need to find the sign in each of those intervals. And we'll write out the factors that make up our rational expression over here on the side. Then we need to choose some test values, some x values from each one of these sections of our number line. So I need something smaller than -7. Let's go with -20, definitely smaller than -7. Something in between -7 and -5. Only one whole number in there, so we'll use it. Something between -5 and 2, and something bigger than 2. You don't have to have those exact same values as me. You just need to make sure you choose something in each one of these intervals. Then we take each one of these values and plug it into our expression over here on the left. -20 plus 5 is negative. -20 minus 2, also negative, and -20 plus 7 is negative. Do the same thing for x equals -6. -6 plus 5 is negative. -6 minus 2 is negative, and -6 plus 7 is positive. 0, we plug in and we get a positive, a negative, and a positive. And then when we plug in 10, we get all positives. To get the final sign, what we're really interested in, we multiply all the signs in each column. So a negative times another negative gives us a negative result. Next column, we get a negative times a positive, which is a positive result. Multiply the plus minus plus, we get a negative, and all the pluses make a positive. Keep in mind or remember that anytime you have an odd number of negatives in your product, you will have a negative number in your result. So what were we looking for? Go back to our original inequality. We were looking for where is this function greater than 0? Numbers greater than 0 are our positive numbers, so we want this column and this column. So look up on your number line. That means we want to go from -7 to -5, and also from 2 to infinity. Since it's strictly greater than, we don't have to worry about our symbols. They're all going to be just parentheses, not including those endpoints. There we go. X values in those 2 intervals will give us a rational expression up there that is greater than or equal to 0. Oh, sorry, greater than 0, not equal to. One more of these, another rational inequality. This one takes a little more setup before we're ready to start solving the inequality because, like I mentioned, we have to have one side of this inequality equal to 0. And then on the other side, we need to make sure we have a single fraction. So first thing I'm going to do, I'm going to start out by subtracting that 5 over x minus 6 so that everything's on one side of our inequality. Then we need to get that common denominator, okay? The common denominator is just going to be x plus 3 times x minus 6. So over here on the left, sorry, not plus 6, we are missing the x minus 6. So we want to multiply that in on the top and the bottom. And our second fraction is missing the x plus 3. So we want to multiply that in on the top and the bottom. So let's simplify what we ended up there. Here we'll distribute that 4, and we have 4x minus 24. Here we'll distribute the 5, but be careful, that sign comes with it. We are subtracting here, so distributing a negative 5 becomes minus 5x minus 15. Whole thing is over that common denominator that we just built. Combine any like terms we have up top. We have a 4x minus 5x, so that's negative x, and a negative 24 minus 15, which is minus 39. And this is really the version I'm going to look at going forward. Okay, that we're going to use that to find first our key values and then to determine our result. So key values happen where the numerator is 0. Be careful with those negatives in there. When we move the 39 over, it becomes positive, and then we divide both sides by negative 1. X is negative 39. There's one of our key values, key numbers. Also, X is negative 3. And finally, X is positive 6. We'll take those 3 numbers and throw them up here on our number line. Again, the scaling doesn't matter so much as long as you make sure you have them from smallest to biggest. Each one of those numbers is the divider of a column that we're going to set up here. And we're going to put our factors that make up our rational expression over here on the left. And then we need to choose our test values. We need to choose numbers in each section of the number line that we just set up here. Something smaller or to the left of negative 39. I'm just going to go all out. That's way over there. Negative 100, definitely less than negative 39. Something between negative 39 and negative 3. How about negative 10? Between negative 3 and 6, I always like to use 0 when I can, and something bigger than 10. Sorry, bigger than 6. I said the number I had in my mind. There we go. We take each one of these values and plug it in for x. Again, be careful with that minus sign there. So we have minus a negative 100, which is positive 100 minus 39, which is positive. Negative 100 plus 3, negative 100 minus 6. Then we put in negative 10. Again, the double negative. Be careful. That's 10 minus 39, which is negative. Negative 10 plus 3, negative 10 minus 6. 0 minus 39, 0 plus 3, 0 minus 6. And then when we put the 10 in there, that's a negative 10 minus 39, which is negative. 10 plus 3 is positive, and 10 minus 6 is also positive. Multiply every sign in each column, and we get plus, minus, for our sign pattern. We were looking for, where is this rational expression less than or equal to 0? Less than would be our negative results. And go up and look at our number line for those columns from negative 39 to negative 3 and from 6 to infinity. So let's write out our result. Now we got to talk about the symbols we're going to use here, because when you see that less than or equal to, you're thinking square bracket, and that's what you should be thinking. But we have to be careful, because remember, we can never allow this denominator to be equal to 0, okay? So let's think about this. The infinities always get a parentheses no matter what. These others, we're thinking square bracket, except we can't allow the denominator to be 0. So we cannot put a square bracket on negative 3 or on 6. The square bracket can only go on the negative 39. There is our final answer. Okay, next, number 21. 2 problems here, part A and B. We're first going to find all the points on the x-axis that are a distance of 4 from the point 3, 2. To do a problem like this, I like to sketch a little picture. I want to see what's going on. It helps me know how to set up my equation. So I'm going to show you guys the point 3, 2 be about there, right? And we want to find all the points that are a distance of 4 away from that. Not all of them that are on the x-axis. So 4 units away, I'm going to kind of sketch it out here. All the points that are 4 units away from that point would make a circle, right? We could go 4 units in any direction. That's roughly a circle, okay? But we're not interested in that whole circle. We are only interested in the points that fall on the x-axis, which would be this one right here and this one right here. So there are 2 of them. Either one of these we can represent. We don't know the x value, where on the x-axis that is exactly. That's what we're trying to find out. But we do know if it's on the x-axis, it has to have a y value of 0. So we're going to use the distance formula. We know the distance has to be 4, and we know these are our 2 points. That's going to set up an equation for us. So here is the distance formula, just in case you don't remember it. Let's start filling in some numbers. The distance is 4, d is 4. x2 minus x1. So I'm going to call this my second point and this my first point. So x2 is x, minus x1 is 3, and we want to square that, plus y2, it would be 0, and y1 would be 2, and we want to square that. Let's simplify. First of all, that big old radical over there, I'm not going to be able to solve for x while that radical is there, so I need to get rid of it by squaring both sides. That leaves me with 16 equals x minus 3 squared. And negative 2 squared, I can simplify that. That's just positive 4. There's more than one way to solve this. You could FOIL out that x minus 3 squared out, but there's actually, I think, an easier way if we just use our square root property to solve this, kind of like we would on a completing the square type of problem. So I subtracted that 4 from both sides. Now, again, I'm solving for x. I need to get rid of that squared. So now I use my radical. Don't forget plus or minus. And the square root of 12 can be simplified. That's 2 square root of 3. And that is equal to x minus 3. Add 3 to both sides. And there we solved it. 3 plus or minus 2 times the square root of 3. That is our x value. Now be careful. Directions say find all points. A point is an ordered pair. So we want to write our final answer as an ordered pair. So we either have 3 plus 2 times the square root of 3 with a y value of 0. There's one of the points. Or 3 minus 2 square root of 3 with a y value of 0. Those are our 2 points. That's what our final answer would look like. Okay, part B, similar, but it's just a little bit different. We're going to draw a new picture so we can see that difference. Now, instead of looking for points on the x-axis, we are looking for points on the y-axis. And the reference point we're using is -4. Positive 3, so about there. This just doesn't need to be perfect, just a rough sketch so we can see what's going on. And again, if we were to look at all points that were 10 units away from that point, it would be a big old circle, right? All the points that are 10 units away would make a circle. Pretend like that's a real circle instead of a bumpy circle. But we're not interested in all those points. We're only interested in the 2 that are on, this time on the y-axis. So this one and that one. Similarly, when we were on the x-axis, it was x comma 0. We're on the y-axis. This time we know the x value is 0, but we don't know what that y value is. That's what we're trying to solve for. So same setup, just instead of x0, we use 0y when we're looking on the y-axis. So for this problem, our distance is 10. So 10 equals the square root of, this time I'm going to use this as 0.2 and this is 0.1. So x2 minus x1 squared plus y2 minus y1 squared. Same solving procedure. I will square both sides to get rid of that radical. And I have 100 equals, and here minus a negative, that makes a positive 4, and when we square it, that is 16. Scroll down and get a little more room here. We're going to solve again in a similar way using that square root property. So we'll subtract 16 from both sides. Gives us 84 equals y minus 3 squared. And take the square root of both sides. Let's see, what's the square root of 84 look like? You could simplify that by hand, but I just like to use my multi-view calculator. It's nice and quick. It is 2 times the square root of 21. Don't forget, since we took the square root of both sides, we need that plus or minus in there. Finally, add 3 to both sides. There's the solution to our equation, but again, it asked us to find the points. So we want to write these as ordered pairs. This time we'll have an x value of 0. And there's one of our points. And then the minus gives us our other point. We get the plus and minus to get both points, the one up here and the one down there. All right, next one. Number 22, find the equation of a line through these 2 points. And then we want to write our answer in point-slope form and in slope-intercept form. Anytime you are asked to find the equation of a line, the most important thing we need to figure out before we can do the rest of the problem is the slope of that line. This one's pretty straightforward. They gave us 2 points, so we can just use our little slope formula. If it helps you to label your points so you can fill in the values easier, y2 is 5 minus y1, negative 2. x2 is negative 3 minus x1 is negative 5. Watch out for all those pesky little negative signs up top. We end up with a 5 plus 2. On the bottom, negative 3 plus 5. Up top, 7. And on the bottom, 2. There is our slope, 7/2. So we need 2 different forms. We need the point slope form, which looks like this. We will use our slope and either one of the points from the problem. It doesn't matter which one. Either one makes a valid equation. Oops, but don't use the x value where the y goes. Then we want a 2 there. Y minus a negative 2, the y value, equals m times x minus a negative 5, the x value. The only thing we need to do here is just those double negative signs. Here is our equation in point-slope form. Oh, but don't put m. Put the number. We calculated that slope for a reason. 7/2 goes there. There is our equation in point-slope form. Now we also need slope-intercept form, which means we can either solve this equation for y, or we can use y equals mxb and one of the points to find the slope-intercept form. We already got this one here. We might as well carry on with it. Let's just go ahead and solve it for y, and that will give us our next result. We'll distribute that 7/2. So we get 7/2x plus 35/2. And then we're going to subtract 2 from both sides. Y equals 7/2x. And 35/2 minus 2. Maybe you don't like fractions so much, so use your calculator with that fraction button. 35/2 minus 2 is 31/2. So there is our equation in slope-intercept form. Next up, we have 2 examples where we need to find the domain of these functions and give our answer in interval notation. As a reminder, domain is the set of all inputs or x values where your function is defined. A lot of functions are defined for all real numbers, but things we need to look out for right now in particular are even radicals, because you cannot take the square root of an even number. And then we also need to watch out for variables in the denominator, because a denominator can't be 0. So for part A, we have both of those things going on. We have an even radical on the top, and we have a denominator. So for that even radical, we have to make sure that whatever is under the radical is not a negative number, so it's got to be greater than or equal to 0. So one part of our domain for part A is going to be that x has to be greater than or equal to -3. That takes care of our numerator, or that even radical. But we also have to watch out for the bottom here. We also have to make sure that the bottom of that fraction is never equal to 0, because division by 0 is undefined. Well, let's factor this one. 18 would be 6 times 3, and to get a -9, we need them both negative. So we have to make sure that x minus 6 is not 0. And we also have to make sure that x minus 3 is not 0. So now we need to put all three of these things together in a single interval notation. If you struggle with that, I think it is helpful to put your results on a number line so you can see what it looks like all together. So this first part, x is greater than or equal to -3. Let's say -3 is about there, okay? And greater than or equal to -3 means it would start here and it would go on and on and on. It would be everything. But that's not our full domain. Two other issues. We need to stop at 3 and kick it out. We need to open circle there. And we need to stop at 6 and kick that number out, open circle there. So to indicate this result in interval notation, we are going to have 3 separate intervals put together in a single result to show the x values between -3 and +3, but not including +3. And then x values between 3 and 6, but not including 6. And then x values bigger than 6. All the numbers that fit in these intervals would be our domain, or our set of inputs where that function is defined. Same setup for part B, okay? Let's work this one. We got to make sure this time that x plus 1 is greater than or equal to 0. Which leads us to x greater than or equal to -1. That will make sure our even radical is okay. We also have to make sure that that denominator is not 0. Can't be 0. So we need to factor here. 20, I think of 4 times 5 first, but a 4 and a 5 can't give me that 8 in the middle. So how about 2 times 10? To get a -10 and a +2. That looks good. So that means that x plus 2 cannot be 0. And x minus 10 cannot be 0. So once again, we need to put all of these three things together. Like I said, think it's easy to visualize them on a number line. I'm going to start with my two bigger numbers first. 10 can't be 10, open circle, do not include that number. And -2 can't be -2. I put some big giant open circles there so you can really see it. Can't be that number either. And then we can look at this. -1 would be here. I'm saying -1 is okay, and anything bigger than -1 is okay. So this time, once we take this consideration, that x has to be greater than -1, -2 is already kicked out by that. So we don't have to worry about -2. -2 is already kicked out of the club because we are starting at -1 and going up to 10. And then we're going from 10 to infinity. X values in these intervals will give us a defined result. That's our domain. Number 24, we have a difference quotient here. A difference quotient is something you use in calculus, but we use it in this class just to practice with function notation and how to simplify functions. So what we want to do, I'm going to do some highlighting here so we can see exactly what's happened. I want to figure out what f of x plus h is, and then I'm going to subtract from that f of x, okay? Remembering that when you have a function f of x, think of that variable in the function definition of just like a fill in the blank. Okay, whatever you put here in these parentheses has to go here and here in your function. So in my parentheses, I have x plus h. That means when I write it out, I'm going to have 3, and then in that first box goes an x plus h squared, and then I have plus 6, and then I have another x plus h. So this came from the first part of that difference quotient. That is my f of x plus h. Then I'm going to subtract from that. Oops. Get my pen going. Subtract from that f of x, which is just the function with no inputs changed. Just write the function exactly as you see it in the function definition. So there is the next part that came from this part of our difference quotient. Then we take that whole thing and we're going to divide it by h. Okay, lots of simplifying we need to do here. Let's start off up top by squaring that x plus h. I'm going to leave that 3 alone. Remember, if you have to jot it down to see it, x plus h, you need to FOIL those out. It's going to be x squared, and then our outer and our inner product together gives us a 2xh, and then h squared. Then we'll distribute that 6. And then we'll also distribute that negative sign because we need to make sure we're subtracting every term. Whole thing gets divided by h. And then next up, we're going to distribute that 3 in the front. Lots of terms here. I know it's a lot to write out, but just bear with me. The rest of it, I'm not changing at all. I'm just copying it down again. Whole thing divided by h. Once you have done all your distributing and squaring and removed all your grouping symbols, then you want to look through your numerator and look for like terms that can be combined. Here is a 6x and here is a 6x, and look at that. One of them is a positive 6x and one of them is a negative 6x, so they cancel each other out. I've got an x squared term here and an x squared term here. And again, one is positive and one is negative, so that goes to 0. That's everything. So let's rewrite what we have left now. Now we have 6xh plus 3h squared plus 6h all over h. We do want to do some more canceling. The thing that you have to be careful with here is we're going to cancel this h, and we've got to do it with every term above. You can't just do the leading term. Division is distributed just like multiplication is distributive, so you need to apply it to each term. So the h cancels with one of these, and one of those. So our final answer, well, the bottom one cancels with all those, so it's gone, is 6x plus 3h plus 6.